Hello to everyone and welcome to this new lecture in my channel. This is States of AI, a collection of lectures about artificial intelligence, machine learning and data science. For who don't know me, I am Matteo Ciprian. I am the owner of this YouTube channel and I am a machine learning engineer working in Cambridge, and I work also as a content creator here in YouTube on lecture about machine learning and sensor fusion, which is my field of expertise. So State of AI is this collection of lecture where I usually invite a domain expert talking about a topic on machine learning or data science. Usually what I ask to my guest is, for a specific topic, what is this topic, why we need this, and what are the state of the art indeed of this specific topic. The target audience for this lecture are mostly professional, maybe expert in data science, machine learning, but not only. It's open to the wide audience of tech experts which are interested in these thematics. So today we will discuss a topic which is I'm actually really ignorant, I have to admit, despite I shouldn't be, because it's a really hot topic at the moment, but I think that it will gain momentum in the next 5 years. That is my perspective, but maybe, I don't know, maybe it's 3 years, maybe it's 10, who knows. So this topic is federated learning. A really brief understanding. So federated learning can be seen as a distributed machine learning approach where basically the training occur in multiple devices and locations. I will not go in deep because we have now an expert that will explain today in deep what is this federated learning, but you can understand that the main application and use case of federated learning is data privacy, decentralized data training, and also edge computing and scalability of the machine learning processes. To talk about federated learning, I invited actually an ex-colleague at my university, a colleague and a friend, Francesco Pase. I know that he will explain his curriculum a bit better, but just a brief overview. So Francesco he has a master's degree in telecommunication engineering, and he's currently doing a PhD in information engineering at University of Padova. Over his career, he has been visiting students in many of the top European universities like the Imperial College of London, and his domain expertise research topics are distributed learning, reinforcement learning, graph algorithm, and wireless communication. So, Francesco, welcome to this lecture, and thank you very much to have accepted my invitation.
Okay, so everyone, thank you very much, Matteo, for the kind introduction, and thank you for having me here. It's a pleasure to be in your channel. So as Matteo mentioned, today we are talking about federated learning, and just a few words about me. So I'm a final year PhD student at the University of Padova. I'm supervised by Professor Michele Zorzi. I'm conducting research on information theory and machine learning, and specifically on distributed learning, federated learning, multi-arm bandits, and personal learning and wireless communications. So before starting PhD, I was an intern at Institute London doing mainly deep reinforcement learning research. And then before that, I spent 1 year at the PFL in Lausanne during my master, where I also completed my master thesis at Learn to Forecast, which is a startup located close to the PFL campus in Lausanne. Last year, I also spent 6 months at Imperial College London under the supervision of Professor Deniz Gunduz. And I'm currently in Cambridge doing a research internship at Nokia Bell Labs. So I'll stay in Cambridge for the summer.
I really hope that you enjoy.
Thank you. Thank you very much. But we'll enjoy the summer together.
Nice. So when you're ready, go.
Yeah, ready to go. So without further ado, I will start by motivating this topic and this presentation that Matteo offered to you. So basically, where we are today, so this is like a very general slide about AI in general and the applications of AI. I'm not a big fan of AGI and, this AI will replace humans and whatever, but I'm still convinced that the kind of state-of-the-art techniques that AI provides to us are still very capable in accomplishing some very important and complex tasks. For example, here you may recognize on the left the prompt of ChatGPT. So I just asked ChatGPT to answer 3 questions. The idea is to summarize the Game of Thrones first season in 1 sentence, 2 sentences, and 3 sentences. So I just asked for the first season without spoiling to the guys who have not watched the entire TV series yet. And as you may see, this is like a very ChatGPT can basically answer very quite detailed responses. And so, nowadays, big institutions, companies are using this model to perform very important, also company-related tasks. Yeah. Now, in the middle, you can see basically a picture that has been generated by AI, where I just prompted the text, Shiba Inu drinking in Venice, and they were able to provide this nice, beautiful graphic about this dog having fun in Venice. And on the right, you can see basically what's happening inside a Tesla car while doing automotive autonomous driving tasks. So here we can see the AI basic application is able to classify, to recognize cars in the street by identifying them with the rectangles. And in the second row, you can see other classification, detection, segmentation. These are all computer vision tasks that nowadays AI is able to solve and to basically outperform all state-of-the-art solutions not based on AI approach. And also the keyboard. So the prediction on the keyboard in your mobile phones, basically those predictions are performed by AI algorithms. And in the right, second row right, you can see the kind of cancer detection that again is provided by AI algorithms that can support the medical doctors in taking some decision. So these are just a few of the many applications that today AI is able to basically bring to the end user. But what they have in common, basically, all the application, is these 3 main components. So they are all based on deep neural networks. So they are all powered by deep neural networks behind them. And they are all based on the fact that they're trained on big data, huge amount of data, very big data. So in order to accomplish those complex tasks, they need to be optimized and trained by seeing a lot of data. And third, computational power. So basically, in order to have prompt responses from these deep neural networks, and also to train these deep neural networks, we need these quite heavy, basically, and high capacity computational platforms in order to perform the training stage, to the inference stage, and so on. So all these 3 components can provide these very fancy and also powerful results in these high-level applications. So just to give you a hint, basically during the famous AI winters, what was missing were basically the big data and the computational power. But the idea of deep neural networks was somehow there, even in the 80s and 90s. But nowadays, we have all these capabilities in our devices. And so that's basically the explosion of this AI field.
Correct me if I'm wrong, Francesco. When we're talking about AI in winter, I think we covered that period of time between the 90s to the 2010, 2011, no?
Yeah, that was somehow basically the last one, because actually there were 2 or 3 kind of AI winters, and the perceptron by Rosenblatt were like mid of the century. So that was the first time they basically researchers started adopting this neural network strategy. And then there was some winter, and then thanks to Geoff Hinton and other colleagues, they were able to find new fundings for the connectionism kind of research, so neural networks. But again, Minsky and other researchers were supporting the kind of symbolic AI reasoning and the stuff, and they thought that this idea of neural network would not work. And then we had all this new hype of AI thanks to all these computational platforms and big data. So yeah, the last one, as you said, basically covered those years.
Yeah, nice. Glad that we passed the winter.
Yeah. Okay. So now the point is that if you think about it, all these data, where these data are collected. So the point is that these data are collected in a kind of distributed way, and also they're kind of private data, local private data. So you may see here, in order to train all these models on nice data like images, MRIs, GPS locations, or all these information are not collected by clouds, are not in the cloud, are not collected by servers. They're collected by the end users while using their mobile devices. You can see here, for example, a smartwatch that can register a lot of biomedical signals like heart rate, or you can see a drone like monitoring a crop field. You can see hospital collecting MRI information on patients, cars collecting images and other stuff. And also, of course, your mobile phone is like a powerful platform to collect data, like all these Spotify, Netflix, all the multimedia applications, keyboard, the camera. So all these data are collected in a distributed way, so geographically distributed, but mainly they are like private data, user data. So this is an important concept to keep in mind. The data are not naturally centralized in some servers, but they're first collected distributively at the end by the end user. So this is the main point. And now, to train these huge models today, the centralized and the standard way of performing this learning strategy is to take all this amount of information, pictures, locations, whatever, and the idea is to communicate all this information to the cloud platform, to a central storage system, and then the usual big tech corporations and other companies, they can exploit all this data to train in a central way to train a huge model and synthesize this neural network that is represented here. And the idea is, okay, if you want to provide those functionalities in the end user device, you can basically communicate back this neural network to the devices so that the devices can use the application. Now, this way is like the standard old style way of doing machine learning. And of course, there are some pros and cons on this basically approach. The pros is that there are a lot of previous works on that. So you can rely on many years of expertise, not just theoretical work, but even how to fine-tune this model, how to find the hyperparameters and make it work properly, all these fancy things. And second, the models can access basically to all the data simultaneously. And this is quite important. We'll see later why. And it is easier to optimize. So what I mean by optimize is, as I said before, being able to find the proper hyperparameters, for example, the network size, the learning rate, or the architecture, if you want to try and then try again. So many times, these huge models, they are trained and they are optimized by errors and trials and errors. So if you want to do it basically quickly, the best way is to have a centralized model where you control, you manage the process from the beginning to the end, and then you can synthesize the best model that you can find on those data. Of course, there are some cons. Privacy is the biggest one, I would say. So this model is not designed to preserve privacy. And this would be the main reason why federated learning is like a huge topic nowadays, because you may think that, so now users, I would say, are more and more conscious about the fact that these big companies are collecting a lot of data from our devices in order to train these huge models. If you want, you can just give your permission, you can do it, that's fine. But the point is that probably in the near future, the user will be not so happy of sharing all the data they are collecting during the days. And also, regulators are starting to introducing into this domain a lot of new rules that these big companies need to basically to match, basically need to respect. So in the near future, it won't be so easy to collect all this data and to perform centralized training. Security is another point. So of course, sharing the data through the network, because this edge here, starting from the data to a central storage system, basically you can imagine this is crossing wireless networks, like mobile cellular networks and all the internet. So of course, if someone can catch your data on the fly, you can basically see your data, and this is not so secure maybe. Communication burden, of course, sharing all the data. So at each time some devices collect new data and you want to further train the model, you need to send all the data to the cloud platform and then to train your model on that. Latency is, again, why I put latency, this is a bit more, there's some more details on that, but the point is, again, if you want to fine-tune your model on the new data that you have, you need to wait until basically your data reach the platform, and then you have to wait for the centralized platform to perform some training strategy, training epochs, send back the model, and then you can use your updated model. So from here, the idea is to design some more distributed approaches. Let me say at the beginning that federated learning is not a brand new technique. Distributed optimization was there since, 70s, 80s, and even maybe before. The point is that federated learning is a kind of well-suited technique to be applied to neural networks and to these AI models that we have nowadays. Nice. So from here, we're moving to the federated learning setting. That is a distributed way of doing the training. Another point is basically this one. So here I will just introduce the idea, then I will provide the details. So the idea is that you can see here we have all these devices that they have locally their model, and they also collecting data. Now the point is that they can train their models using their private and local data in order to be to accomplish what they have to accomplish. But the point here is to exploit all the data of the other devices in order to enhance the capability of your model. That's why in the centralized setting, you put all the data to the cloud platform. And so what Federated Learning is doing, basically the idea is to upload, instead of the data, to upload the models themselves, you can see here. And then the central authority will basically take all this model and synthesize a new global model that somehow contains all the information collected by all the end users by this using these devices, and then basically send back this new global general model to the users, to the devices, that they can further use and train again on local data. So here, as you may see, the private data never leave the device, but just the model. So instead of communicating data, you communicate models back to the server. Now, there is also a third kind of option that is the decentralized federated learning, where there is no more the central authority, but you perform federated learning by point-to-point communication between devices. But this is, I would say, still kind of open research area, and there are not, I guess, practical application of that. But still is an interesting kind of research topic.
Sorry, Francesco, on that point, can we define this like a peer-to-peer federated learning, this new version?
Yeah, exactly. So this can be thought of the distributed. That was the decentralized.
Okay.
Decentralized, can be like a peer-to-peer federated learning. So there is no central authority.
Okay, got the point.
Models, but just you can send the models to your neighbors, and the neighbors of neighbors.
I got the point. Yeah.
Okay. Exactly. So the pros of this is that of this framework is that, of course, this is designed to preserve privacy because, again, data never leave the devices. You can see this symbol that I will say, we'll explain later why it's not 100% like this, but at least it is designed to preserve privacy. Whereas centralized setting, there is no way to preserve privacy of the user. Security and communication efficiency, again, we have this symbol. I will explain some details later. But the point is that, again, you're not basically communicating the data, so they cannot be stolen by external kind of malicious attackers. And you don't have to send huge amount of data to the cloud. And the latency is because you always have your model locally. And if you want to train your model quickly on new data that you may have, you can exploit those data to train your model and to use it for inference, so for run your AI-based application. The consequence of this, of this is that basically it is harder to optimize. Why? Well, because in this way, if you want to do some trials and errors, hyperparameter tuning, you need to be orchestrated. That need to be orchestrated by the server, but you need to inform all the devices to do some sort of new optimization, or to use a new optimizer to do that. And you will see the effect of this after a while, because you need all these devices to perform this training, and then you need to collect back the updates. So it's not like straightforward as having all the process central in a central kind of entity. And you have not direct access to all the data. And again, I will explain later what's the drawback of this.
Yeah, I can imagine a lot of problem here, especially in the last point. I think
exactly.
I don't want to go too further because I'm pretty sure that we will cover this in the presentation. But I can, if I think some application in my specific domain, which is a kind of digital healthcare, where actually we try to go more in this kind of explainability paradigm, where basically not only on the model but also on the data. So provided the data where the model has been trained. Yeah, I can see some problem here on this last point. Exactly. But yeah, maybe.
Yeah, by the way, feel free to discuss if you have some new insights on this, because we can further enhance these slides with some nice discussion about your expertise. So that's nice. And explainability is also something that I did not put here, but as you mentioned, I think it can play a role in federated learning for future applications.
Yeah.
For real world application, actually.
Okay. Thank you.
So these are the kind of brief introduction of how it works in the specific. So basically the idea of training the model, during the slides, I will put all the references, like the main references or some of the topic. Of course, there are a lot of them now. Federated learning, you can find thousands of new papers appearing every week. So you can, if you feel free to contact me if you want to know more, to have more details or references about that. But so here I'm just sticking to some of the well-known researchers and papers about the topic. So this is the way how it works to train the model. So you can see it works in round, and do until convergence is like, okay, you repeat this for many rounds until you reach the convergence. So by convergence, I mean until your model, is well trained, so your loss doesn't decrease anymore. You cannot increase the accuracy, and you have quite a good model. So each round of federated learning starts like this. We have a server that distributes a global model to the user. For example, you can start from a random model as usual in the machine learning. You just imagine distributing this global model to the user. Each user then trains locally for some epochs using stochastic gradient descent, basically by using the private data. Sorry for the typo in the slide, but the idea is basically that each user now can use stochastic gradient descent to perform some training of the local model.
Okay.
So basically, global models at the user side. It can be 1, 2, or 3 that we will discuss later. And then once the user has trained the model locally, the user will send back to the server this model. It can be the model itself. It can be the gradient computation that accumulated during these local epochs, or it can be the difference between the old model and the new model, whatever kind of information. And the server will then aggregate all these model updates, for example, by taking the average, and send this new aggregated model to the user back. And you keep going like this in other training rounds until you reach convergence. So this was first proposed by McMahon and in this kind of milestone paper that opens the doors to federated learning applied to deep networks. And basically, empirically, they observed that it was working very, very well. And so this is one of the main cited paper on the topic because of this is a milestone for this research field.
Nice.
So this is actually mathematical, if you want, formulation of that. I just put this slide just to have an idea of what's going on behind the hood. So the idea is, let's say that we have a model like a deep neural network that is parameterized by W, where W is the model parameter vector, for example, the weight of neural networks. And this omega star is the optimal set of parameters, set of weights that you want to find that is basically the one that solves your problem, the one minimizes your loss. So this is the argument of not just the loss on one model, but the loss on K clients. You can see here. Yeah. So you have the set K collects all the clients by clients or users. I will use them interchangeably. So the idea is that you minimize the sum of the loss for each user. And now the loss is basically, as you may know, in machine learning in general, you don't want to minimize just the loss on your training data, but you want to minimize your loss in this test data, where test data is a new data sampled according to the user-dependent distribution. So basically, D of K is the data distribution of user K.
Yeah.
And the idea is if you have a new sample, like a new data sample where X is the input, Y is the target label, imagine supervised learning, the idea is find basically the best model that can minimize the loss on a new sample. So these are the generalization capabilities of the learning models. But the concept basically is that you want to minimize the loss of a global, find a global model that minimizes the loss for all the users. And all the users may have different decay. So that's the main point, because decay is a distribution of the local data. So you may have some user having exactly the same decay, but some users, they may differ. And so this is the goal of federated learning. Now, this paper, basically the first solution, and I would say the skeleton of all the solutions that you may find out there in federated learning, they all relies on this first solution, this federated averaging. So federated averaging that was first proposed again in this paper works like this. If you see here, you start from a global model that is WO, and this global model basically is first distributed to the user. Actually, in each round, you don't need that all the users participate in that round. So you can sample like a subset of the users.
Okay.
And so this is to make it more communication efficient, and you don't need all the users to be available during the same round. So this is also in practice very useful. Just stick to the main points of the algorithm. I don't want to go to all the details, but the idea is that you sample a random set of clients, and for each client, they will perform some client update to find a new WK of the client. And T+1 is basically indicates the round. So you start from WT, the initialization model for round T, and you end up in a new model parameter WT+1. And then, so this is basically to collect how many users and how many samples per user you are collecting. But the point is that the global W here, as you may see, is just a weighted average of all the local models. It is weighted by, for example, you can scale it by the number of samples each client has with respect to the number of samples of all the users. Okay. So, for example, if we are all performing local training with the same number of samples, then we have uniform sampling, uniform weighting. If you have many data, you're training on many data, I have less data, the idea is that my kind of update basically has a lower value with respect to your update. So this is just like a weighted average for that. And as you can see, the client update, so what's going on locally, is to perform some very standard stochastic gradient descent epochs. So you start from W, you compute your gradient or an approximation of the gradient by using a batch of samples. This eta is the learning rate, so you perform some epoch from from 1 to E. E is the number of local epochs in this algorithm, and then you send back this W to the server. So this is basically the skeleton of all the Federated Learning solutions. You send this model, you perform stochastic gradient descent locally, and then you send back this to the server. The server will aggregate all these parameters by weighting those updates, for example, by using the ratio of data they're using.
I have a question, actually. Yeah. Maybe I've lost something, but is there a specific reason you're using stochastic gradient descent here, or the same theoretically could be done also with a gradient descent, no? Or is there maybe some convergency or a reason? I don't know. So
yeah, this is like a whole field of research. So there are many papers, many findings. But yeah, the question is important. So the idea, for example, is, if you want to, you will never get to the gradient of that function, right? Because you cannot have the infinite amount of sample. But this is actually what they're kind of observing here. So on the right, you can see the results of this technique, the very first, very preliminary result they obtained with Federated Learning. So this is exactly federated SGD. This again stochastic. So the idea is that basically machine learning, we will never get access to the true gradient, right?
Yeah.
You always get some samples. You try to approximate the gradient by using, for example, a batch of data. And even though all your training data set, it won't cover 100% the distribution that you want to cover. So that's why basically they use stochastic gradient. But the idea is also that you don't need to go through all the data sets to perform the local computation. You can just use, PKs, batches of size B. So basically a computer gradient, as you said, like by using just finite or basically smaller batches of samples. And this will speed up the convergence. In terms of, so basically the local round will last less because you just perform training on a part of the data node. You don't go over all the data to perform one epoch. So this is important. And here you can see, for example, on the right, the accuracy that you can achieve, and also the time that you need to achieve that accuracy while basically modify number of E and B. E is the number of local steps. B, so here you can see here, the number of epochs. B is exactly as you can see again here, the size of the batches that you're using to compute your kind of approximation of the gradient. So initially there was this, federated SGD is like performing SGD without having this new idea of, so they're using just one local iteration because that was all distributed optimization kind of strategies. And you have infinite, meaning that you use all your data or all your statistics to compute the local gradient. Now, what these researchers basically try to exploit is to perform many epochs locally and to decrease also the batch size so you can speed up your training kind of round. As you can see here, you can speed up basically your the time that you need to convert to an accuracy of 99% here and 54% here. Now, of course, it's not like linear. This is linear in U, where U basically is this expected number of updates. But that is like some other details about that. I won't go into this. But the point here is that you can see that by increasing E, so performing more local updates, and sometimes decreasing B, so having just batches with smaller sizes, you can speed up a lot of the convergence. And this is basically what Federated Learning is relying on. Kind of subtle detail that I want to highlight here is that not always increasing E, like the number of local epochs, will help. Because one can say, okay, but then I can have E equals to the number of training iteration I need. And so locally, they all perform like, you can start from a model, you perform local training until the end, and then you aggregate these models in the end. That won't work. because of course, locally, your gradient will diverge one from the other from each user. So you need to basically to get to the same point every once in a while, and then to really distribute the model. So this is a key important concept of federated learning. And it is more, basically it is more relevant in the non-IAD setting. So again, I use this slide to explain what I mean by IAD and non-IAD.
Okay.
So IAD means that all the data are distributed in the same way over all the clients, over all the users. So meaning that the statistics of my data set is the same, or the statistics of the data set of all the other clients. Non-IAD, that is the more practical and real world case. The idea is that you may have different statistics. So your data is not exactly distributed as my data. Just to give you an example, imagine I'm in this data set, we have 10 classes. And then imagine that IAD means, okay, I take the data set, I uniformly sample one of the data and give it to all the users. So basically that is uniform distribution of the data. Non-IAD means that, okay, I can give to that user all the data only on two specific classes, like number one, number two. So that user will always see only basically the images of a number one or number two. And for another client, maybe 4 and 5. So they have different statistics, right? Because they are seeing different part of data. But by using federated learning, you can make the other user that has just locally 4 and 5s, for example, also to perform well, even if it sees an 8, because it's learning from the knowledge acquired by all the other users. So this is the kind of main idea behind it.